Assalamualaikum warahmatullahi wabarakatuh. Today we're going to cover extrusion process and also wire and bar drawing process. So we go for the extrusion process first. In this part, we're going to cover extrusion process, and in part 2, we're going to cover wire and bar drawing process. Extrusion process is a process where the work material will be compressed and forced to flow through a die opening to produce a desired cross-sectional shape. So this process is similar to the squeezing of the toothpaste. Okay, so it is like that when you have a opening and then you squeeze out the material to come out through that opening. Okay, so in general, extrusion is used to produce long part of uniform cross section, meaning that the part is have certain design, but it has to be uniform cross section throughout the length. Okay, so we have two basic type, which are direct extrusion and indirect extrusion. On under direct extrusion and indirect extrusion, there are two type, which is the solid and also um, what we call a hollow part. Okay, so meaning that if we want to divide it become four type of extrusion. So here is direct extrusion. So if we look into the operation here, um, this is the container. Okay, so if you can see, this is the container, and then there are also the die opening over here. Okay, so and then this is the work material, starting material, and this is the final product. Okay, so this material will be pushed by the ram with the force. Okay, and then it will be coming out from the die opening over here. So in order for you to understand the direction for the direct extrusion, the force um, direction and also the direction of the work material is the same, then it is called direct extrusion. For indirect extrusion, the material will be coming out on the other side, meaning that it will be the inverse of this force. Okay, so we're going to look into the indirect later. So here is the animation for the direct extrusion. So you will see that this is the extrusion process where you push the work material through the die opening, and there will be a leftover material that cannot go into the die opening. So that one is called butt, P-U-T-T. Okay, so that part will be removed from the final product. The direct extrusion, it is also called forward extrusion, and the starting work material is a round billet, and for the cross-sectional shape, it will determine by the die opening shape. Okay, so a ram will approach the die opening, and a small portion of the billet remain that we cannot force into the die is called the butt. Okay, so this butt will be separated from the work part that we produce. So for direct extrusion, the previous one, what we show to you is the solid work part. Okay, so apart from the solid one, we can also create hollow part like this one. So in order to get the hollow part, they are going to have a mandrel in between the ram here, so that the hollow part can be produced. Okay, so in here, hollow and semi-hollow shape can be produced depending on the opening of the die. Okay, so direct extrusion to produce hollow or semi-hollow cross section, and C is the semi-hollow cross section. Okay, so this is the final product. This is hollow and this is semi-hollow. Now let us see how the process take place. So if you can see here, so there's a mandrel in between the product, so then in between the ram here, so that it will create the hollow part inside the work material. So here is another example. This is the mandrel, and then this is the final product that coming out. Okay, so if you can see, it will create a tubular with a hollow shape at the end of the product. So for indirect extrusion, so it is to produce a solid cross section and also a hollow cross section product. So if you can see, the difference will be the direction of the work material that coming out. It will be inverse of the direction for the force. Okay, so once you give the force over here, the product will come out in between here. Okay, in the center here. And as for the hollow part, it will be like this one. Okay, so for the indirect extrusion, it is called also backward extrusion. This is because of the how the workpiece come out after the extrusion process, where it is inverse to the force. Okay, so meaning that it is reverse in direction, so it is also called reverse extrusion. So the limitation for indirect extrusion is it is lower rigidity of the hollow ram, because if you can see, it is going inside the work material direct, so there is low in rigidity and difficult to support the extruded product also. So that's why for the indirect extrusion, the length of the workpiece is considered shorter compared to the direct extrusion. So for the advantage of the extrusion, the variety of shape is possible to be produced, especially if it is a hot extrusion. But the limitation will be part cross section must be uniform throughout the line. You cannot change the shape of the workpiece in between of the operation. Okay, so the grain structure and strength will be enhanced in cold and warm extrusion. It can also create a very close tolerance, especially in cold extrusion, and in some operation, little or no waste of material involved. In extrusion, there are hot extrusion and cold extrusion also, the same like the previous process. So for hot extrusion, the work part will be heated first, and then when it is heated, it will reduce the strength and increase the ductility of the metal. Then more size reduction or complex shape can be produced via this process. As for cold extrusion, usually used to produce a very discrete part. Okay, so the term impact extrusion is used to indicate high speed cold extrusion. So for extrusion parameter and analysis, in extrusion ratio, we call reduction ratio, where because there will be reduction of the cross sectional area compared to the starting cross sectional area. So this is calculated by using this equation, Rx equal to A naught over the A final, where the A naught is the cross sectional area of the starting billet and AF is the final cross sectional area. So this one is applies to both direct and indirect extrusion. So for the strain, it is calculated like the previous one also. So epsilon equal to ln Rx, where it is ln A naught over the AF. Okay, so we can also calculate the pressure in the process, okay, for the ram. So this one is calculated by average flow stress times the ln Rx. Okay, so then you will get the pressure. Again, the average flow stress is calculated by using this equation. Okay, so if we consider the friction and all, we have to use the equation given here, which is epsilon x equal to A plus B ln Rx. Okay, so A and B is usually given. It is an empirical constant for the given diangle. So the normally the constant will be A equal to 0.8 and B is 1.2 to 1.5. Okay, So this one is the A and B value tend to increase with the increasing of the die angle. Okay, so by using the Johnson's extrusion strength formula, we can calculate the ram pressure, which is YF times the epsilon x. So in direct extrusion, we cannot prevent the effect of the friction between the container wall and also the billet. Okay, so this usually caused by the ram pressure um, for the which is greater for the direct extrusion compared to the indirect extrusion. Due to that, we can use this equation to calculate the pressure and also additional pressure required to overcome the friction. So this equation includes PF, which is the additional pressure required, by the node squared over 4 is the cross-sectional area, equal to the this one is the what we call the coefficient of friction on the container wall. PC is the pressure of the billets against the container wall. Okay, and pi d naught L is the area of the interface between the billet and also the container wall. If the worst scenario happen, so assumption on the stress equal to the yield strength happen, so this equation will be is produced, and then if we assume that the ys is half of the average flow stress when the pf is reduced to the following, so that the PF will be reduced to this equation. Okay, PF equal to YF to L over D naught, so that we can simplify the equation for the PF, for the PF. Okay, so then based on the reasoning, the following formula can be used to compute ram pressure. Okay, so then we can calculate the ram pressure using the P equal to YF epsilon x plus 2L over D naught. Okay, so then we can also calculate the force, okay, using this equation. This is the same like previous one, and then P power is calculated by using P equal to FV. Now let us look into the effect of die angle to the ram force. Okay, so when the die is big in angle, okay, my apology with the line because my stylus is not working properly. It's broken actually. Okay, so if it is big in term of the um, angle here, okay, let's say the alpha is big, what happen is when the material is pushed by the ram through this area, there will be a turbulence of material in this area because the angle is too big, so that the flow of the work material into the die orifice will be very difficult. Okay, so then the ram force will be higher. Okay, so if the angle is small also, it will be very difficult also to the process where the ram also will be higher. Why? Because there will be too small area for the material to flow into the die opening over here, so that will cause extra force for the ram. Okay, so that's why what we need is the optimum angle instead of big or small angle. Okay, so that's why at optimum the ram force will be at the minimum compared to when the alpha is low or alpha is big. So for the die angle, as mentioned previously, low die angle will give a surface area larger,
then it will increase the friction at the die billet interface. Therefore, there will be higher friction result the larger ram force. As for the large die angle, there will be more turbulence in metal flow if we use a large die angle. So this one also will increase the ram force required to push the workpiece to come out from the die opening. So in here, lowest die angle or highest die angle doesn't give a good result. So the most important thing is to find the optimum range of angle so that the product can be flow smoothly coming out from the die opening. So this one is depending on the work material, the billet temperature, and also the lubrication of the process. For the shape of extrusion die orifice, the simplest cross-section of the shape will be circular die orifice, and shape for the die orifice will affect the ram pressure. Of course, as much more complicated um, the die orifice, and much more ram pressure also will involve. Okay, so as cross section become more complex, higher pressure and greater force are required, and effect of cross section shape on pressure can be assessed by means of the die shape factor Kx. For the calculation process for the pressure, it involves the shape factor, okay, Kx in here. So therefore, for the calculation of the P, we have to involve with the Kx, okay. And so for indirect process, it is calculated by P equal to Kx Yf and epsilon x directly. But for the direct extrusion, it will calculated by using this equation, P equal to Kx Yf epsilon x plus 2L over d naught. Okay, so this one is for the direct extrusion. Okay, so this Kx is calculated by using this equation. Okay, so Kx equal to 0.98 plus 0.02 Cx over Cc with the power of 2.25, where the Cx is perimeter of the extruded cross section and Cc is the perimeter of a circle of the same area as the extruded shape. Now let us look into the problem. A cylindrical billet is 150 mm long, 75 mm in diameter. It is reduced by indirect extrusion to a 30 mm diameter. Okay, so the starting is 75, and then is indirect extrusion to 30 mm diameter. The die angle is 90 degree. In Johnson equation, A equal to 0.8, B equal to 1.4. So in flow curve for the work materials, work material strength coefficient equal to 800 MPa, and strain hardening exponent is 0.15. So what you have to determine is extrusion ratio, true strain with the homogeneous deformation, and then extrusion strain, and D is ram pressure, E is ram force. Okay, so you have 5 questions that you have to solve. For A, you have to calculate the reduction. Okay, so Rx equal to A naught over AF. So quite simple. So you can just simplify the equation. It becomes D naught squared over df squared. So you will get the value 6.25. Okay, and then you have to calculate the homogeneous through strain. So epsilon equal to ln Rx equal to ln 6.25, so you'll get 1.833. So the next one is the one with the friction with the Johnson equation. So you can calculate by using A plus B ln Rx. So A is given, B also is given, so you can just replace into the equation and you will get the value 3.366. Now, the D is you have to calculate the pressure. So pressure is you have to calculate the YF times the epsilon X, right? Remember the equation for the pressure. So then you have to calculate the YF first. In here, YF is calculated by using this equation, 800, 1.833 with the power of 0.15, and then over the 1.15. So then you'll get this value, and when you put it into the equation for the pressure, then you'll get this value. Okay, so the final one is force. So the force is calculated by using the pressure time the area. Remember? Okay, so then pressure you already have the value, and then the area, so you just calculate the value for the cross sectional area, and then you will get the value for the force. So here is another problem. So as for this problem, you try to solve it on your own. And here is the solution also for the question. You can refer to the solution after you already tried. This is the example on the product that has been extruded. Okay, so it shows the complexity of the product that can be produced. So here are some example of the extrusion product. Okay, so they are solid and also hollow part. So finally, this is the link to the videos for you to look into. So you can refer to the link to look into the actual process.
So that's the end for the extrusion process. Thank you very much for listening. Assalamualaikum.